So put things in perspective. So we started with a Hod conjecture, which showed that assuming there was an extendable cardinal, we have this dichotomy theorem between V and Hod. That's very much like the dichotomy of Jensen's covering theorem. And then the key question is how to interpret this. Is this an indication that that the Hod dichotomy is not true and that there's an ultimate version, say, of L? That's a definable construction which pushes Hod close to V. And then, or is it an indication that intermodal theory fails at, say, supercompact? So that's the key issue. So, and then the scenario for proving the Hod conjecture would be to extend intermodal theory to supercompact, build a weak extender model for supercompact that's definable. Presumably that would be as a fine structure construction, and thereby prove the Hod conjecture. So we don't know which way it's going to turn out, and it's worth noting that if the Hod conjecture is actually true, there's nothing that suggests it couldn't have an easy proof. I mean, if you think about it, the Hod conjecture is saying that Hod must be either very close to V or the Hod dichotomy theorem is saying that Hod must be very close to V or very far from V. There's no middle ground. So if you could somehow prove that Hod was somewhat close to V, it would have to be close to V, say in the context of an extendable cardinal. Well, Hod is somewhat close to V. It's Hod after all. Every set is set generic over V, over Hod. So maybe the right twist on Vopenka could enable one to prove the Hod conjecture. Okay. All right, so the first idea to build a weak extender model for supercompact is try to generalize Kunin's construction of L mu, and we showed that the Martin-Steele sequences are a natural attempt for that, and that fails. Then we look more deeply at the current form of inner models, partial extender models, and I showed a technical thing that indicates in the current methodology that there's a problem there. So now I'm going to drop down to the infinite levels of supercompact and focus on a specific issue. So I'm going to give you a little bit of an idea of what fine structure looks like. I'm not going to use this very much. I'll use it a little. So the situation is we have the language of set theory augmented with two predicates. Think of bold P as the extender sequence and P as some presentation of an extender at an active stage. So we're looking at models of the form J alpha of P, P restricted to, or structures, J alpha of P, P restricted to alpha, and then the last thing. And P alpha is supposed to be a subset of J alpha of P. And this naturally defines a structure for our language where we interpret this predicate by P restricted to alpha, and we interpret P dot by P sub alpha. We're only going to be looking at transitive structures, and if I have a structure, I'll denote the interpretation of, I shouldn't have used P and P since we can't talk in fonts, but I did. Bold PM is the interpretation of that, and P sub M is the interpretation of that. All right, so now we're going to expand our language. This is following ideas of Magador, and this is the current template. We expand the language by adding three area predicates, Tn for every n, every finite n bigger than 0. And now we're going to look at a very special class of formulas instead of looking at arbitrary formulas. So a formula phi is a sigma 1 formula of our language, of our enhanced language, if it's just a sigma 1 formula relative to the base language. Here's the key change. A formula is sigma n plus 1 in our restricted sense if there's a sigma 1 formula of the base language such that theta has this very specific form. Basically, it's asking, you're allowed to quantify over Tn and then just say something sigma 1 about what you get. Okay, so it's always sigma 1 definability, but you're allowed to grab complicated information. And what's going on is this is enabling one to handle the higher levels of definability as one would handle the first level. And that's very important in the analysis. Okay, so I'm just making a lot of definitions. For each formula of, I think I have a slight misprint here. I'll go back. Yeah. So for every formula of our enhanced language, we add a Skolem term. SKN is the smallest collection of terms closed under composition for the nth level terms. And a formula is now a generalized sigma n formula if it's obtained by the substitution, the free substitution of n level terms into a sigma n formula. So naturally, I'm really defining a new language, but I don't want to do that. It's really an L++, okay? So now we have to say how we're going to interpret these, and that's done by induction. So if we have a structure, we're going to define by induction on n the interpretation of the new predicate, something called the nth projectum, which Martin has already talked about, and the interpretation of the Skolem terms. And then I'm going to be very picky. If I write this, I mean that, well, misprint, but so I'm not being too picky. Indicates that these are the free variables are included in that set and so forth. All right, so here are the definitions. We have our structure. Suppose we have an nth level formula and that tau is a corresponding Skolem term. Then for every m tuple, the m tuple is in the domain of the term and b is the value of the term if first m satisfies phi at our parameters together with b, but for all c less than m in the natural order that m has, phi satisfies not phi. M satisfies not phi. So the Skolem term is just picking out the least witness. All right, for every subset of the field of the structure, the n theory of X is simply the set of all generalized n-level formulas with parameters from X which are true in M. So remember, the n generalized allows the occurrence of the Skolem terms. And then the projectum, the nth level projectum, is the least ordinal, less than or equal to rho, such that the n theory of rho together with some parameter is not in the structure. Okay? Okay, that's it. Now I have to define the predicate. So the interpretation of Tn is it holds at alpha qb if and only if alpha is less than the nth projectum, q is in the field, and b is the n theory. The n theory is present by definition of the projectum. That's the whole point. And if the nth projectum is 0, then the construction stops because it doesn't make sense. Okay, so it takes a while to digest it, but you can see what's going on. The Tn are representing fragments of a complicated theory. You're allowed to look at a fragment and say something about it. All right, so I now have to introduce hulls. This is all in the notes, so don't worry about it. If M is a structure and we have something in the field and we have an n bigger than or equal to 1 less than omega, and the nth and the kth projectum of M is bigger than 0 for all k less than n, well, that means we've defined everything at the nth level. So the n hull is just closure under the n level terms. And we can take the transitive collapse and get a new structure. Okay, in the obvious way. What? There isn't a projectum. The constraint on the projectum, this constraint, is only so that the nth level things are defined and everything. Okay, I'm not taking the hull of the projectum on anything, just taking a hull of a set. All right, so this is just a standard template. If you open up or look at any article in fine structure theory, it'll look like this. Now, suppose M is an amenable M structure. That means that predicate P sub m, all of its initial segments are in the model. I did define that. Then, m is omega sound if for every k plus 1 less than omega, one of the following holds. Either k is bigger than 0 and the kth projectum is 0, in which case the k plus 1 theory is not defined, or there exists an element of the model such that the model is the k plus 1 hull of the kth plus 1 projectum together with A. Okay, so as long as your projectum is defined, you have to be a hull of that ordinal and some point of the model. And now the projectum might keep dropping. It might go all the way down to 0, or it might stabilize. Okay? Look, if it's a structure that if it is a structure which models the FC, then it's omega sound, because all the projecta are the height of the model. And so this ordinal would be the height of the model, in which case this is trivial. So this is like, well, anyway. All right. If m is amenable and omega sound, and the kth projectum is bigger, let's suppose we have an amenable omega sound structure and that the kth projectum is bigger than 0, well then we can do something interesting. We'll let rho be the kth projectum, and we'll fix the element of m, which we could take to be an ordinal if we wanted, such that m is the k hull of rho together with q, and we can now form a new structure. The new structure is n. We take m restricted to rho, that makes sense, and t, where t is just the k theory of rho together with q coded as a subset of m restricted to rho. And that's an amenable structure, right? Because the bits of the theory are all there since it's the kth projectum. So we've taken, and now here's the key point. N is also omega sound, but its first projectum is the kth plus 1 projectum of m. Further, if we take a subset of m restricted to rho, then the following are equivalent. It's sigma 1 definable over this new structure from parameters if and only if it's k plus 1 definable and m from parameters. So what's happening is you do a one-level analysis, and in the situations where you're going to use this, that's really the key case. Because when you're trying to analyze the higher levels, you can just repackage the structure into an equivalent structure where the things you're trying to analyze, namely the k plus 1 definable sets, are just the 1 definable sets in the new structure. So it keeps taking you back to sigma 1. And so that's the power of sound structures. And that's all through the theory. And that's the whole point. It's iterated sigma 1 definability is all that's going on. All right. So now let's suppose we have a predicate contained in ord cross V. We'll say that J of P is amenable if for alpha in the domain of P, the following hold. I don't need this, but it makes me more comfortable. So we'll say sigma 1 replacement holds. So we're only going to have something in the domain if sigma 1 replacement holds at that stage. P alpha is a subset of the alphth level. And for all beta less than alpha, P alpha intersect J beta of P is in J alpha of P. So when you're in the domain, when you add that set, all of its initial segments are already present. Furthermore, you're adding it over a level which looks nice. It's a model of sigma 1 replacement. Okay, so then we'll say that a predicate, suppose that we have an amenable predicate, we'll say J of P is sound if for every alpha in the ordinals, this structure is omega sound, and if alpha is in the domain of P, then this structure is omega sound. Both of these are L structures, and so this makes sense. All the levels are sound. So I have two sorts of levels of this. I have the levels where alpha is not in the domain of P. So I'm viewing it as an L structure where I just interpret the last element by the empty set. And I have the levels where alpha is in the domain of P. So I have my L structure. And I say that's omega sound. Okay, so I'm just defining when a class model is amenable. I defined it when it's amenable. We're constructing from this predicate. I'm now defining when it's sound. Basically, its levels are sound. Okay, soundness is a very strong form of GCH. It is a form of GCH. Suppose P is contained in OR cross P, J of P is amenable and sound, then the GCH holds in J of P. That's an easy calculation. All right, so here's a lemma we're going to sketch, and this will be this is the easy lemma. Sorry. Suppose kappa is kappa plus omega supercompact, and P is a subset of V kappa. Then you can find delta less than kappa in an elementary embedding pi, where first of all pi is in V kappa. The critical point of pi is delta. Gamma is the omega plus 1 successor of delta, and pi of gamma is the omega plus 1 successor of the image of, that's a typo, that should have been a delta there. Okay, but so this is like a rank to rank embedding from a small rank up to a big rank, like omega extendable say, but notice that it's requiring that we're moving P correctly. Okay, it's just saying we can find rank to rank embeddings as long as we don't move too many power sets past the critical point, which cohere P. Okay. No, pi is in V kappa, so pi, the critical point is, yeah, I just dropped both. You know, so we've got V kappa like this, and we've got some predicate P, and we're trying to find an embedding like this. This is a critical point. This is the image of the critical point. We've got, this is H delta plus omega plus, so we're going up to the omega plus 1 successor, to the omega 1 plus successor here. But when I take the irrelevant part of P, it's being moved to the relevant part of P. It's cohering P. Okay? All right, so this is just, it's an easy argument. Kappa, remember what our assumption is, kappa is plus omega supercompact, and we have GCH, so I've already said it must automatically be kappa plus omega plus 1 supercompact. Take an elementary embedding that witnesses that. Critical point of J is kappa. M to the lambda is contained in M, where lambda is the omega plus 1 successor, which is the cardinality of that, which is the cardinality of that. In N, let M be J of M, and let J of J circle J be the iteration embedding. And now if you look at what's going on in the final model, J restricted to this is here, and that's here, witnesses the conclusion of the lemma at J of J circle J of kappa for J of J circle J of P. So you just go 2 steps, and you see enough of J to witness it, so that means the theorem was true in B. The usual thing when you use supercompact. You're trying to prove something, you apply the embedding. The only difference here is we're going 2 steps out and verifying that J of J circle J of what we're trying to prove is true in the final model, so it's true in the initial model. All right. So here's the theorem, whose proof I want to sketch. This will be the only proof I do that takes more than 2 slides, and it's not hard. And it's a really good exercise in understanding the basic fine structure, so in this very general sense. Suppose we have a predicate, and J of P is amenable and sound, then in J of P there are no cardinals kappa which are kappa plus omega supercompact. So that means you cannot build an enlargement of L that reaches the level of kappa plus supercompact by any kind of amenable and sound construction. That's the point. Okay, so we're going to work in this inner model. So everything is as calculated in this structure. Remember, it's amenable, so we have GCH now. So we assume toward a contradiction that there is a cardinal kappa that is kappa plus omega supercompact. And by the previous lemma and the fact that we have GCH, we can find a delta less than kappa in an elementary embedding that's coherent pi. And here I did have the pi of delta correct. Pi of gamma is the omega plus 1 successor of pi of delta. So we have a shift. All right? So as Menachem points out, and you will discover if you ever try to do this, giving a proof of PowerPoint is really hard, right? Because you can only put so much on a slide. And so you jump to the next slide, and then everyone's forgotten what everything is on the previous slide. It's almost like you want to be able to have the 3 previous slides available. But anyway, now we're going to let eta be, remember, gamma is the omega plus 1 successor of the critical point, and pi of gamma is the omega plus 1 successor of the image of the critical point. So we're going to let eta be suit pi image gamma. And if you think about it, it's pretty easy to check that this structure is a model of ZFC plus power set. Okay? So the first claim is you can't have a closed subset of eta whose cardinality is less than the omega successor of the image of the critical point, such that C is cofinal in eta and C intersects psi's in J eta of P for all psi less than P. Well, let's see why. Suppose you had such a set. All right, well now we can let D be the set of all psi less than gamma, such that pi of psi is in C. Now D is omega closed because pi is continuous at omega limits, and by 1, because C is cofinal in eta, because C is cofinal in eta, D has to be cofinal in gamma. Remember, gamma is the omega plus 1 successor. So we can choose something in D such that D intersects psi 0 has cardinality greater than or equal to delta plus 1. Because D has cardinality delta plus omega plus 1. It's cofinal. It's an omega club, cofinal in the omega plus 1 successor. Oops. All right, so C intersect pi of psi naught covers the image. And by 2, the power set of C intersect pi psi naught in J eta of P. Because the eta of P has all sets, has all the bounded subsets of pi of delta. So we see this in J eta of P. But that implies that pi image delta plus omega is in J eta of P. And so pi restricted to H of delta plus omega is in J eta of P. But that says that pi of gamma is definable from parameters in J eta of C. There's a singularizing function. This is a contradiction because eta is the sup of pi image gamma, and this is a model of replacement. Okay? So this is an easy and standard argument. It's the proof that square fails. Okay, but repackaged slightly. All right, so that proves the claim that we can't have a club in eta, singularizing eta, all of whose initial segments lie in this structure. All right, but now we're going to let alpha bigger than eta be least, such that for some k less than omega, the kth projectum of M is less than eta, where M is this structure if alpha is not in the domain of P, and M is this structure otherwise. Remember, V is J of P. So as we construct, eventually we have to collapse eta down. And now we're going to assume that alpha is in the domain of P. The case that alpha is not in the domain of P is easier. Okay, so we're going to fix K now to be least such that the kth projectum of M is less than eta, in which case the kth projectum of M has to be pi of delta plus omega, because M has all the bounded subsets of pi of delta plus omega. So the projectum can't possibly fall below. Remember, the projectum is where you're missing a set, namely a theory. But M has all the bounded subsets of pi of delta plus omega, and so the projectum cannot fall below. It has to hit pi of delta plus omega, and that's really the whole point. We have two cofinalities, right? This has cofinality omega, but eta has cofinality delta plus omega plus 1. And it's going to be the collision between those two that difference that leads us to a contradiction. So the first claim, and this is the main claim, is that K has to be bigger than 1. It cannot be the first projectum. All right. Well, let's assume toward a contradiction that it is the first projectum that takes us down to pi of delta plus omega. Well, by soundness, a little misprint, there exists a parameter in J alpha of P such that M is the one hull of the first projectum, which is that cardinal, together with Q. Well, how do you generate the hull? You generate it by closing under terms. You can take a universal set, and so you get a partial function from pi of delta plus omega, that's the projectum, and it's a surjection onto eta, such that F is generalized sigma 1 definable in our structure from parameters, just by definition because of this. All right, now remember our generalized formulas have those Skolem functions in them. Skolem terms in them. And they're not sigma 1. They can be changing their values because they're looking for the least. So, but the claim is that, and this is where the first case where we're going to heavily use amenability, is that we can reduce to the case that F is just sigma 1 definable. So the idea is, I didn't write out this proof, is we have approximations. I'll be doing this shortly anyway. We can take this structure and for beta less than alpha, just truncate it. Or we can replace P alpha by P alpha restricted to some beta. And we can do a series of approximations and interpret the Skolem functions there. Well, as you're allowed to look at more of P alpha, the value of a Skolem function can change. Because it may say, wait a minute, here's a smaller witness. But it can only change a finite number of times. You can't keep getting smaller infinitely often. So this is a cofinal function. So for every one of ordinal in the domain, the Skolem, there are only finitely many of the Skolem terms that can appear in the definition, they're each changing. Might as well assume there's just one Skolem term. So for everything in the domain, there's some number of times it can change. But then there has to be a single number, some I, such that if I look at I changes, that gives me a cofinal function. Right? What we're doing is partitioning the domain into omega many pieces. The ith piece is where the Skolem term changed I times. The function restricted to one of those pieces has to be cofinal because the cofinality of eta is uncountable. Cofinality of eta is delta plus omega plus 1. So if I restrict, so then I can replace my definition by sigma 1 definition. I look for I changes. And I just take the value I get after I changes. Now on that piece where the term changed I times, I'm getting the value of F. On the other pieces, I'm getting who knows what. But the new function is cofinal. And I can turn it into a surjection easily. So we can reduce to the case that it's sigma 1 definable. So let's fix a sigma 1 formula and a parameter that defines the function. Okay? Now I'm going to require that this formula has a special form, which I can easily do. It has the form, there exists psi less than alpha, such that psi holds at x0, x1, x2, the initial segment of p alpha up to jc of p, where psi is a sigma 1 formula that doesn't mention the predicate p dot. That's the interpretation of the last predicate. Okay, that's the predicate for p. So I can easily take any sigma 1 formula in the language, and in this case I can require it has this form. All right, so we're going to fix an ordinal large enough to collect the parameter that we need. And now for every beta between alpha 0 and alpha, we're going to define an approximation to f. We're going to let f beta be the set of all b in j beta of p, such that this structure thinks psi holds at a, b, psi naught, and p alpha intersect j psi of p for some psi less than beta, such that this belongs to jp of beta. So instead of allowing myself to look at all the initial segments, I'm restricting the initial segments to something present, and I'm restricting the structure as well. All right, so it's just easy to check, well, it's trivial to check that f beta is in j alpha of p and that f beta is contained in f. It's also easy to check that f is the union of these. So what we've done is written f as an increasing union of functions that are in the model. Remember, f is not in the model. Okay, so now we have two cases. Let's suppose that the cofinality of alpha is not delta plus omega plus 1. Well, then there has to be a beta less than alpha such that the range of f beta is cofinal in eta. Okay, but f beta is in j alpha of p, and that contradicts the choice of alpha. Okay. Remember, eta is a cardinal in j alpha of p. It's the omega plus 1 successor of pi of delta plus omega from the point of view of j alpha of p. Case 2, the cofinality of delta plus omega, cofinality of alpha is the cofinality of delta plus omega plus 1. Alpha is the stage where I've projected and collapsed the omega plus 1 successor of collapsed eta down to pi of delta plus omega plus 1. So remember, okay, I need those 4 slides. So now we let theta be least here such that f of theta has range cofinal in eta. There has to be one because this is coph omega. So now you're seeing a collision between two different cofinalities. Thus, the cofinality of theta equals the cofinality of eta is delta plus omega plus 1. Now we fix a subset of theta of cardinality delta plus omega plus 1 such that f restricted to x has cofinal range. We have that h pi of delta plus omega is contained in j alpha, so clearly x is in j alpha of p. It's a small bounded set. Therefore, there's an increasing continuous cofinal function g from delta plus omega plus 1 into eta, such that g is sigma 1 definable from parameters in our structure, and such that g restricted to psi is in j alpha of p for all psi less than delta plus omega plus 1. Well, now let C be the range of g. C satisfies the conditions of our claim. It singularizes eta, and all of its initial segments are in j eta of p, or j, and that's a contradiction. Remember, we showed that you can't singularize. There can be no club that singularizes eta in its true cofinality, which is delta plus omega plus 1, all of whose initial segments are in J eta of P. Well, G is such a thing. Okay? The fact that G restricted to theta, the fact that G restricted to size in J alpha of P means that it's actually in J eta of P, because eta is cardinal from the point of view of J alpha of P. Okay? So I mean, that's hard to follow, but you can kind of get an idea, I hope, how we used amenability. All right, but we just handled the first level. But remember, we can repackage the higher levels into amenable structures, and that's exactly what we're going to do. Okay, so now that proves claim 2. So we prove that K is bigger than 1. That was claim 2. So now we let n be K minus 1. Well, so we have the nth projectum of m is bigger than eta because K was least, such that the nth projectum of m was less than eta. So either rho n of m, the nth projectum, is alpha, or it's a cardinal of J alpha of P, bigger than eta. Let rho equal the nth projectum. Fix a parameter such that m is the n hull of rho together with P. And now we look at this structure. We go only up to rho, the nth projectum. We let T be the n theory of m of rho together with Q, coded as a subset of rho. And by that useful fact about soundness, the first projectum of n is the nth plus 1 projectum of m, which is the kth projectum of m, which is pi of delta plus omega. And for some p in J rho of P, n is the 1 hull of the first projectum of m together with P. And now we can just repeat the proof that K was bigger than 1 and get a contradiction. We're just changing the structure. And we're done. Okay, so, and this is how fine structure typically works. You have a first level argument, and then you repeat it for the higher levels. Okay? So that proves that if you present V by a predicate which is amenable in sound, you cannot have suit cardinals which are plus omega supercompact. All right, so how about if we weaken the amenability condition? So suppose alpha is in the domain of P and alpha is a limit ordinal, then we'll say that this structure is omega weakly amenable if P is a subset of omega cross J alpha of P, and for each n less than omega, for some limit ordinal gamma n less than alpha, the nth section of the predicate is contained in J gamma n of P and all of its initial segments. Well, I'm not going to require that they be here, just in the parent structure. So in an omega weakly amenable case, instead of having a single predicate of height your structure, all of whose initial segments are in, you have omega many predicates, each cofinal and possibly different initial segments of your structure, and their proper initial segments are just present in the parent structure. Okay, so if P is a subset of Ord cross P, then P is weakly amenable, or J of P is, if for every alpha in the domain of P, the structure is omega weakly amenable. Okay? Now, when I do fine structure theory for non-amenable structures, we have to alter the definitions a bit. So let's let's reduce our language. L minus is L obtained by eliminating the predicate for P, the top predicate. And now here are the definitions. We now say a formula is restricted sigma 1 if there's a sigma 1 formula of the reduced language such that theta looks like there exists x is a subset of P dot, x0 is finite, and phi holds. So sigma 1 now is only allowed to look at a finite subset of the interpretation of the top predicate, and then say some sigma 1 fact about it where you're not looking at the top predicate. If you look at the Mitchell-Steele book, this is how they defined restricted sigma 1. And then we just make the obvious definition. Your restricted sigma n plus 1, if there's a sigma 1 formula of the reduced language, and then otherwise it's the same. Okay? Now the notion of soundness is exactly as defined for the case of amenable P, but one uses this revised definition of n formulas. Now for the amenable structures, this amounts to replacing P with P star, where you keep the domain the same, but for each alpha in the domain of P, you change P alpha to just be its set of initial segments. So quantifying over the initial segments of P alpha is like quantifying over the finite subsets of the set of initial segments. So there's no change. You just change how you present the predicate. Okay, and then we can define soundness the same way. JP is sound if for each alpha in the ordinal, M is sound where M is either of these structures. Now, if P is contained in ord cross V and J of P is sound, then GCH holds in J of P. Okay, I've already observed that. We've already observed that. Okay, now to analyze the omega weakly amenable, instead of going through what we just did, we're going to do something else. So I'm going to bring in square. So this is Jensen's weak square. Weak square holds at kappa. If there's a sequence indexed up to kappa plus, such that for all alpha less than kappa plus, C alpha is a closed subset of alpha of order type at most kappa. If the cofinality of alpha is less than kappa, then the cardinality of the club is less than kappa. And if you look at the collection of intersections, it's bounded by size kappa. So we're looking at C beta intersect alpha, beta less than kappa plus, then that set has size at most kappa. So we're not requiring coherence. We're just requiring there are not very many initial segments. Okay, so I've wanted to define very weak square, but Foreman and Magador stole that phrase from me 20 years ago. So I'm going to define weak square, or weak squared squared. Weak squared square holds at kappa, again, if you have a sequence of subsets of kappa. For all alpha, C alpha is contained in alpha, and for all limit alpha, it's a closed cofinal set, again, of order type at most kappa. If the cofinality of alpha is less than kappa, then the club is of size less than kappa. And then for all psi less than alpha, C alpha intersects psi is equal to C beta intersects psi for some beta less than alpha. But I want to call it, yes, I'm about to say that. This is usually called the approachability property at kappa plus, but it's not defined this way. So I'm defining it this way as a generalization of square. Approachability property is more cumbersome to write, and I'm calling it weak square. Call it the approachability property if you want. It's first studied by Shallah. Then in the introduction, where Foreman and Magador define their very weak square, they note this, and it's an easy exercise. Suppose kappa is an infinite cardinal, then the following are equivalent. Weak square holds at kappa, or the approachability property holds. This is the approachability property. But when you use it this way, and that's why I chose this approach. Okay? So this just says that whenever you take an elementary substructure of H kappa plus plus, of cardinality kappa with kappa contained in X, you can find a closed cofinal set in X intersect kappa plus, whose order type is less than or equal to kappa, and if the cofinality of X intersect kappa plus is less than kappa, then C is size less than kappa, and all of its initial segments are in X. That's why it's called approachability. But again, the use is through this. Okay? All right, so soundness in GCH. Suppose P is contained in ord cross V. Then the following are equivalent. J of P is a model of GCH, and you can reshape P to a P star such that JP star is sound, JP is equal to JP star, and the reshaping is sigma 2 definable. So GCH is just modulo global choice reshaping V to be presented by a sound predicate. So there's a nice generalization of this to the weak square or the approachability case. Suppose P is contained in ORD cross P and J of P models GCH, then the following are equivalent. For every uncountable cardinal K, weak square holds at kappa. There is a predicate P, a reshaping, all of whose levels are amenable and sound. There's a reshaping, all of whose levels are omega weakly amenable and sound. So there's no difference between weakly amenable or omega weakly amenable. Looks like a much weaker condition than amenability. But in this kind of generality it isn't, and it's exactly equal to this. So just as soundness is equal to GCH, GCH plus weak square is equivalent to being presented by a predicate all of whose levels are amenable and sound or omega weakly amenable and sound. So everything collapses. Okay, now this proof will be in the notes, and it's just an elaboration of the argument that I gave. So it just takes a little bit of work. All right, so as a corollary, we get that if you can present V by a predicate which is omega weakly amenable and sound, then there can't be any cardinals which are kappa plus omega supercompact. Well, why? By the previous lemma, you can reshape to present P as an amenable and sound predicate, and we already showed that if you can present V by an amenable and sound predicate, there can't be any cardinals kappa which are kappa plus omega supercompact. Okay? All right. So let's go back to good extender sequences. Recall that if we have an extender sequence and alpha is in the domain of the extender sequence, then E is a good partial extender sequence at alpha if the following hold, where E is the partial extender E alpha. J alpha V is strongly acceptable. It's a model of ZFC minus power set. It's E is a J alpha of E extender. E is the Jensen completion of E restricted to its generator's natural length. And alpha is the length of E alpha and the coherence condition. Okay? And now I'm going to introduce the weak initial segment condition. If you have a good partial extender sequence, and you take the ultra power embedding given by the extender given by some alpha in the domain of E, then we say E satisfies the weak initial segment condition at alpha if E alpha restricted to sup eta. It should have been, that's a typo, that should have been JE of eta. E alpha restricted to JE of eta is in J alpha V for all eta less than iota of E eta. That's the space. So basically, this model, the ultra power model, sees all the proper initial segments of the extender. It's a very natural condition. And what's the connection? If E is a good partial extender sequence which satisfies the weak initial segment condition at all alpha, then for all alpha, E alpha can be coded by a set E such that for some beta less than or equal to alpha, well, first beta is less than the natural length, and where we're doing the coding is a model of sigma 1 replacement. E is a subset of that, and this structure is amenable, and these two structures are logically equivalent. So this structure is simply a reshaping of this. Okay. It just turns out that once you go past the finite levels of supercompact, Jensen indexing doesn't give you amenable structures anymore, but you can reshape into amenable structures in a nice way. So here's the best positive theorem today. To assume there's an extendable cardinal, and we're assuming the iteration hypothesis, then there's a good partial extender sequence E such that the following hold. J of E is weakly backgrounded and weakly sigma 2 definable. It satisfies comparison, which I defined last time. For every psi, there exists alpha such that alpha is in the domain of E, and E alpha witnesses omega extendability. and E satisfies the weak initial segment condition at all alpha in the domain of E. And then the levels of J of E are omega sound modulo reshaping. And the reshaping is only necessary where your extenders are witnessing omega extendability. At the finite levels, you don't need to reshape. So that's a positive theorem. But these observations show that you can't generalize this theorem. Okay. Now, I want to leave you with I'm hoping that, don't get your hopes up. It's another 10 minutes. But I do want to give you a nice test question for inner models, or for weak extender models, which is easily stated. So we can generalize a formulation of comparison to arbitrary inner models. So we can do that as follows. Suppose n is a weak, and I'll do it for weak extender model. Suppose n is a weak extender model for delta supercompact, and n satisfies V is equal to hot. So in n, everything is ordinal definable, so we can talk about finitely generated structures. Then we'll say that n satisfies comparison if whenever we take two sigma 2 elementary substructures of n, the following hold where these are the transitive collapses. First, these are each finitely generated and themselves models of ZFC. They have the same reals. Then there's a transitive set n star and two elementary embeddings, which are each close to the respective models. So that's how you would naturally define. Remember what close meant. Close meant take any point here, pull up, look at the ultrafilter induced, then it's in this model. Okay, so that's a very nicely stated test question. It's not clear. And now you can ask, can a weak extender model for supercompactness satisfy comparison? So what's the tension? The tension is it's a weak extender model for supercompact. So there are going to be many different countably generated substructures, and yet they somehow all have to be connected. All right. So what's the summary? Going beyond the level of omega extendable cardinals, which we can reach modulo the iteration hypothesis, requires allowing the weak initial segment condition to fail, allowing levels which are not even omega weakly amenable, and there are many natural attempts for trying to get to the omega, to kappa's kappa plus omega supercompact by using omega weakly amenable, and those must fail. And you have to allow allowing how comparison is proved if one can reach supercompactness. It can't just be comparison by least disagreement. Okay, so the claim, therefore, is we cannot just use good partial extender sequence. A natural alternative is to augment extender models with their iteration strategies, and these are strategic extender models. So I'm going to give you a brief epilogue. Okay, so this is the picture that seems to have emerged. At the lowest levels, past measurable cardinals, the fine structure models can be simply defined, L mu, and there's no distinction between the extender and strategic extender hierarchies. As you go up to the levels below that of one Woodin, there's still no distinction between, at reasonable closure levels, between extender and the strategic extender hierarchies. However, the fine structure models are no longer known to have a simple definition. If you pass one Woodin and up to the finite levels of supercompactness, the extender and strategic extender hierarchies strongly diverge, but both exist and are weakly amenable hierarchies, but exist, well, you're too fast, Menachem. Existence within the extender hierarchy requires an iteration hypothesis, and existence is still open for the strategic. Remember, I'm saying this is the picture that seems to be emerging. I didn't say it has emerged. So this is the guess. Reaching beyond the finite levels of supercompactness requires a complete failure of amenability. Now, amenability is important, and you already saw an instance of that. And there's a very good analogy with descriptive set theory. When you have an amenable structure, the sigma 1 truth predicate is a norm, and it's calibrated by the initial segments. And that plays an important role through the whole analysis. And when you drop that, you run into serious problems. And it's funny, it's only the first level. Because the minute you go to the higher levels of definability, you do have amenable structures. So the whole problem is to define that first level so that it can survive to the second level and that the analysis can survive. And that's where you have to tolerate non-amenability. The sigma 1 truth predicate is no longer a norm, and that corrupts everything. But there are natural ways to try it. Finally, at some point past the finite levels of supercompact, the extender hierarchy fails and one is left with just the strategic extender hierarchy. Okay. Well, I claim we can define, so now I'm going to give you a definition of V as ultimate L, even though we don't know how to define hierarchy. And that seems kind of silly, but I want to observe you can define the axiom V equals L without knowing the definition of L. In the context of a strong cardinal, which is a limit of Woodin cardinals, there are naturally defined approximations to ultimate L, and the collection is rich enough to make this definition possible, even though we don't know the level-by-level definition. So here's the definition of V equals L that doesn't discuss the definition of L. V is equal to L if and only if for every sigma 2 sentence, if phi is true in V, then there's a countable ordinal alpha such that n satisfies phi, where n is simply the intersection of all ZFC minus power set models of height alpha. Well, it's trivial to see that's equivalent to V is equal to L. But notice there's no definition of L here. There's no level-by-level definition of L. So this is silly, but not really, because it says if you can find the right test models, you can express an axiom even though you may not know how to define the class model. So determinacy is the salvation here. So remember, a set is projective if it can be generated in finitely many steps from an open set by taking images and complements, images by total continuous functions. A set is universally bare for all topological spaces and all continuous functions. The preimage of the set has a property of bare in the domain space. This is all spaces. So this is a notion that couples into arbitrarily large sets. Suppose that there's a proper class of Woodin cardinals and every projective set is universally bare. So this is an abstract generalization. In fact, if you have a proper class of Woodin cardinals and A is universally bare, then every set in L of A and R is universally bare. So they have very strong closure properties. So what's the connection? Suppose A is universally bare, then we let theta of L of A and R be the supremum of the ordinals onto which you can map the reals by a function in L of A and R. This is a measure of the complexity of A. Suppose that there's a proper class of Woodin cardinals and A is universally bare, then theta of L of A and R is a Woodin cardinal and the Hod of L of A and R. Now, I should have stated, and I didn't, that under this hypothesis, L of A and R is a model of AD. So choice is failing here, but of course it's not failing here. And though this ordinal looks quite small relative to this, it's of an approximation to the continuum, in the intermodal Hod, it's a large cardinal. So Hod L of A and R denotes Hod as defined within L of A and R. L of A and R models ZF, in fact AD in this context, but certainly the Hod satisfies ZFC. Now assume there are infinitely many Woodin cardinals with a measure above, then for many universally bare sets A, Hod of L of A and R has been verified to be a strategic extender model. So these are the natural examples. The natural conjecture that this must be true for all universally bare sets. But the universally bare sets are not limited because they refer to V. So that makes the axiom, here's the natural guess for the axiom for V as ultimate L. It says there's a strong cardinal, which is a limit of Woodin cardinals. That's a very modest large cardinal hypothesis. For every sigma 3 sentence phi, if phi holds in V, then we can reflect it into one of these test models. So there's a universally bare set A, such that if we take the Hod of L of A and R and truncate it to the theta of L of A and R, that's the Woodin cardinal here, it satisfies phi. We can't reflect into Hod because Hod thinks it's L of a set. So we want to cut Hod where the richness of Hod stops. Well, the richness of Hod stops at theta. The Hod of L of A and R is always L of a subset of theta. So you don't want to go past theta, but theta is a Woodin cardinal in the Hod. And so you expect full richness below that. So that's why we're doing the restriction. Now, because this axiom is, so if this, remember the idea is we know for many examples of A, like A is empty, this is a strategic extender model. In fact, even with A empty, this is not an extender model. It's a strategic extender model. And as you move to more complicated A, the divergence gets significant. So that's the candidate axiom, even though we have no level-by-level construction. But because of the connection with determinacy, we can use all the machinery of determinacy and analyze this axiom a little bit. So assume V is ultimate L. The continuum hypothesis holds. More interestingly, assume V is ultimate L. You can prove V is not a generic extension. So that's kind of surprising, right? It's hard to see V is not a generic extension. In fact, if you take the partial extender models of Mitchell and Steele, any iterable any partial extender model, including the ones I built at the finite levels of supercompact, if they're an iterable model and have a Woodin cardinal in them, they are a generic extension of another fine structural model. So that makes this more interesting. You can also show if V is ultimate L that V is equal to Hod. This is actually open in the extender models. There are examples known where it fails, but even if you eliminate the trivial counterexample, it's not known. As opposed to L, which knows V is equal to Hod. The trouble is partial extend, oops, can't go on. So here's a question, does V is ultimate L imply comparison? In that abstract sense that I defined. All right, so the key question, of course, is there a generalization of Scott's theorem to V is ultimate L? But now we can just state the obvious conjecture. Suppose, and that's the ultimate L conjecture. Suppose delta is an extendable cardinal, then there is a transitive class N. N is a weak extender model of delta supercompact. N is contained in Hod, and N satisfies V as ultimate L. By the universality theorem, this would imply there's no generalization of Scott's theorem. So it's all coming down, I think that was the last slide. It's all coming down to this conjecture. We have the axiom, we have the conjecture, we know what you have to prove. And we know how it's got to look. We know how we can reach the finite levels of supercompact with extender models. The amenability, comparison, all of those are clues that point how you have to go forward. And you have to go forward in the strategic extender hierarchy, and there are just not many options now. And so instead of being in a situation where one's not making progress because there are too many directions to go, and some lead to dead ends, but you don't realize that until you spend 2 years down that path, there's only one way forward now. And so one can write down the definitions, and it's just a matter of seeing that it all works. So though it looks like everything I was saying was negative, this doesn't work, this doesn't work, this doesn't work, in the end, well, it's positive. What's certainly positive is I think we're going to know the answer one way or another fairly soon. If you can prove the ultimate L conjecture, that's one answer. But there's so much information now that maybe there's going to be an anti-intermodal theorem. And that would be a resolution, maybe not the resolution I'm hoping for, but I just want to know the answer. I don't care what the answer is. So it's not a negative picture. All of this, everything I was talking about. So before all this recent stuff, can I go 2 more minutes? The scenario was you build the extender model first. And then after you've done that, you build the strategic extender model. And that's how the strategic extender models have been built, and they've been running into a problem. Okay? And the problem is that's not the right way to do it. You don't try to build the extender model first and then layer it with the strategy. You do it all at once. And that just, and the comparison argument says you can't do comparison by least disagreement. That's what was blocking the attempts at doing the strategic extender hierarchy. You're trying to do comparison by least disagreement, but what if you see a disagreement in the strategy? So there's a clear way forward now, and all those obstacles are swept aside. And it's just checking whether it works. So it's not negative. It's a time of, it's a pivotal time. I think we're going to see the answer one way or the other in the next year or two. And I'm not quite sure what that answer is. I have to say, in developing the theory at the finite levels of supercompact, at least 10 times I thought I'd shown the model doesn't exist. But each time there was some case that I'd overlooked. That's the trouble with fine structure theories. You have to check all of these cases, and danger can lie in any case. And you just have to check every single one. Anyway, thank you for your attention. I'm sorry I went over. And there will be notes. I'll send them to Asaf probably next week. And they'll have all the proofs that I didn't give, and hopefully not as many misprints. So thank you. Down at the small cardinals, things should be well, like one would expect. But there's some very interesting possibilities, which would be quite interesting. Above, this ultimate L has this preferred point. Imagine that we had ultimate L, this weak extender with a supercompact. So we'll have this preferred supercompact, the one that's tied to the extenders on the sequence. And then above that supercompact, we've got everything by universality. Well, it's not clear to me that in the context of ultimate L, if you have, well, the first supercompact is strong compact. It's not at all clear that if there's another strong compact above, that must be supercompact. So maybe supercompact is equiconsistent with strong compact, but two supercompacts is not equiconsistent with two strong compact. Ultimate L will provide the setting for that. You just have to figure out what's going on in ultimate L. And you can do this for all kinds of questions. If you want to compare two large cardinal hypotheses, they each can hold in some level of ultimate L, so you just go to the first level. That should be your comparison. So there'll be a methodology for comparing any two large cardinal hypotheses. It's not clear what that will yield. The trouble is there's something, and this is a meta-mathematical problem. The large cardinals that exist in ultimate L, the supercompact, they weren't put there. They just got there. So why are they there? In inner model theory, you have large cardinals in the inner model because you put them there. Well, that's why you always have a Scott's theorem. But once you reach supercompact, if you can, it's a phase transition. Above the supercompact, you get everything, and you don't put it there. It's exactly like that. But it's not clear. All of the intuitions for analyzing the relationship, you don't build an extender model for huge. You would build an extender model for supercompact. So the intuition that two supercompacts should be equal to two strong compacts, I don't think holds up in this environment. Right? It's got to be a completely different mechanism. Because the model is built with only that first supercompact. And then you're saying, well, the second supercompact, a second strong compact flows into the model only because it happened to be supercompact? That seems, I don't know. I'm just saying there is a whole, you can literally take any two sigma 2 sentences that can hold an ultimate L, and you can compare them by the first levels. So any large cardinal hypothesis formulated in terms of embeddings by universality will flow into ultimate L. So you can compare any two large cardinal hypotheses by just looking at the least mouse. And that's how, for example, you show various, inaccessible Janssen is equivalent to Ramsey in consistency strength. They're not equivalent in V, but when you go into an inner model, they are. So, yeah. So it could be that, no, but I'm just saying the intuition that the old intuition was you'd have two strong compacts. You then do your core model construction. The first strong compact gives you a supercompact or close to it in the K, and then you keep putting extenders on above, and the second strong compact gives you the second supercompact. But in the ultimate L scenario, you're not putting any more extenders on. Right? When you build that inner model with the first supercompact, everything stops. So the intuition that the second strong compact should give you a second supercompact because it's giving you extenders which you'd be putting on your sequence is wrong. So I don't see why you could argue that two supercompacts and two strongly compact. I mean, I don't know. I'm just saying here's an answer that can't possibly be independent. Here's a question. Assuming the ultimate L conjecture is true. Go to the first level of ultimate L that has two strong compacts in it. Does it have two supercompacts? That's not going to be independent. All right? That's like asking, go to the first L alpha where something happens. All right? So these questions that are there that you can't see because of V, you now have a crystalline setting in which to explore these questions. Right? There's not going to be, you can't use forcing. Right? Forcing, ultimate L is immune to forcing just like L is. The axiom V equals L couples the width of the universe to the height. And the only ambiguity you have is the height. And what's the height? Large cardinals. So that's what ultimate L as an axiom is doing for you. It should be reducing everything to height. And so now you can just go through and investigate these questions. And you'll see patterns possibly in the ultimate L context, and there are many possible examples, which are invisible in ZFC because of forcing. So there'll be connections in the setting of V as ultimate L that you don't see otherwise. Maybe that will be interesting. Anyway, that's the long answer to a short question.